The second half of Unit 10 focuses on complex numbers, which may seem unrelated to our polar coordinates. However, you will quickly find the link. For today's notes, we've got learning targets 7 through 11, plotting complex numbers in the complex plane, finding the trig form of a complex number, converting complex from trig form to standard form, finding the product of complex numbers, and finding the quotient of complex numbers. First thing we have to start off with is, what is a complex number? Normal complex numbers are in the form a plus bi, where I is that square root of -1, the imaginary number. So a is the real part and b is the imaginary part, which makes this the complex number because it is part real and part imaginary. A plus bi is the standard form of the number. And over the next several days, we're going to do some powers of these complex numbers. So I just want you to quickly remember what I stood for, the square root of -1. So if you square it, you're going to get -1. So I squared is actually a real number, -1. If you cube it, you'd multiply by the square root of -1 again, and you get negative square root of -1, or negative I. And then if you multiply by the square root of -1 yet again, you're going to get a positive 1. So I to the fourth is positive 1. If you just keep going up the powers, it's going to keep repeating the same pattern. Okay, so what you see over to the right is what our new coordinate plane will be for complex numbers. We have the real axis, which is the x-axis, and we have the imaginary axis, which is the y-axis. So your A and your B kind of act like your X and your Y. You kind of plot A and then your BI if you're plotting these as points in the complex plane. If I have the complex number -2 plus 3i and I wanted to plot, on the real axis I would have gone left 2, and on the positive imaginary axis I would have gone up 3. So you've got 1i, 2i, and 3i. So -2, 3i in the coordinate imaginary complex coordinate plane would be in that second quadrant. So essentially the difference here is that our y-axis is now the imaginary axis. Okay. Trig form of complex numbers is changing this a plus bi, the standard form, a plus bi, into r times cosine theta plus I sine theta. So this red formula is the trig form of a complex number. And here's where it ties so closely with polar coordinates, because you'll see in my picture here I have the exact same picture that we've been using in polar coordinates, where our point is either xy or r theta, and we can tie those pieces together just using some basic right triangle trig and Pythagorean theorem. So if you recall, our A, which was our x here, A, is going to be r cosine of theta. Our B, because our imaginary axis is our y-axis, is r sine of theta. These are just the formulas that we'd already used. Our r is going to be the square root of a squared plus b squared. That's coming from Pythag. We get to make up the trig form, so we're just going to focus on the positive square root so that we have one value. It's not asking us for all the possibilities, so we're just going to use the positive r in this case. And then tangent of theta, using that ratio again, is the opposite over the adjacent, b over a. And if you were to solve for theta, you'd have inverse tan of b over a. So essentially my b is replaced my y, my a is replaced my x, but I'm using all the same formulas that I had from polar coordinates. Okay, so on to the examples. Find the trig form of the complex number. It asks you to find it for theta between 0 and 2 pi. So we're going to start off by plotting the point. 2i has no real part. So all I've got is really 0 plus 2i, which means over 0 and up 2i. So I've got a point up here at 2i. My goal is going to be to find the trig form, so I need an r and a theta. Well, to solve for r, we use the same process we used to. R squared is going to be 0 squared plus 2 squared, my a plus my b, which is going to be 4, which means r is going to be 2. In our polar form, we would have done plus or minus 2 so that we had both options. But here, since we just get to make up our point, we're just going to focus on the positive. Our theta we should be able to figure out pretty quickly because this is a quadrantal angle. So think about your r being a positive 2. What angle would you have to rotate to get to that 2i point? Well, you'd have to rotate a theta of pi over 2, or 90 degrees. I'm writing it in radians because my question asked me about radians. Once you've identified your r and your theta, you plug it into trig form. Trig form is, so here's my standard form, and that's going to be equivalent to the trig form. 2 times cosine of pi over 2 minus plus I sine of pi over 2. Example 2. Start off by plotting that in the complex plane. Positive 1 will go right 1. Negative square root of 3i is going to go down. Negative square root of 3i. Okay? So our point is sitting in the fourth quadrant. Our goal is to find the r and theta that match there. So we start off by solving for r. R is going to be the square root of 1 squared plus negative square root of 3 squared, which is the square root of 4, which gets us 2 again. Okay, so I know I have an r value of 2. Then I have to find my angle. So I use my inverse tan of opposite over adjacent, and I get my angle. Tangent is negative in S and C. But I get to eliminate even further because this time I know I'm only using positive r, and I know I want my point to be in the fourth quadrant. So I'm just going to focus on this quadrant. My opposite's a square root of 3, my adjacent's a 1. That should be easily recognized as a 30, 60, 90 triangle, 60-degree reference angle, which is pi over 3's. You have to figure out how many. Well, 2 pi would be 6/3, and this is 1 short. So my theta is going to be 5 pi over 3. So if I go positive 2 and rotate 5 pi over 3, I will match to that point. Now we write our standard form, 1 minus square root of 3i, as trig form with r times cosine of theta plus I sine of theta. Example 3. Go a little faster this time. Okay, start off by plotting your point. Negative 3, negative 4i is going to be in the third quadrant. Negative 3, negative 4i. It's going to be in that third quadrant. We start off by solving for r. R squared is negative 3 squared plus negative 4 squared, which is going to get us 9 plus 16, or 25, which is going to get us an r value of 5. Again, we focus on just the positive because we get to put it together. Then when I go to find my theta, I take the inverse tan of the opposite over the adjacent. The negatives are going to cancel, so I'm looking for a positive tangent. Okay, so I eliminate S and C, and based on the quadrant that I know my point should be in, I know I'm really looking for an angle in this third quadrant. I do not recognize the ratio 4 over 3. It's not one of our special right triangles, so I'm going to have to use my calculator. Because it asked for radians, we're going to use the calc in radian mode to find this angle. When I do, it's going to give me a theta of 0.927. 0.927 radians is a first quadrant angle. So it gave us the other option. We know that that is our reference angle, so we know that's sitting here. So to find this full angle, I'm going to do pi plus theta. I use pi because that's the radian equivalent of the 180 degrees that I would go before I got to my theta. So if I add pi to get the third quadrant angle, I get theta of 4.069. And then I use my r and my theta to rewrite the standard form in trig form. So negative 3 minus 4i equals 5 times the cosine of 4.069 plus I sine of 4.069. Okay, moving on. Now we're working backwards. Now we're writing the standard form of the complex numbers. And this is really easier than the other way because all you really have to do is distribute and simplify. So this 5 gets distributed in and I end up with 5 cosine of 60 plus 5I sine of 60. And then we evaluate. Since 60 degrees is on our unit circle, we're going to evaluate using our unit circle. I'm actually going to use the song, sine, cosine, 45, 30, 45, 60, 1, 2, 3, 3, 2, 1, 2's under everyone, square root where there is no 1. Okay, so we can quickly come up with this. 60 degrees is a first quadrant angle, so it should be positive. Cosine of 60 is 1/2. And sine of 60 is square root of 3 over 2. You could also have drawn the special right triangle for yourself. So I end up with 5/2 plus 5 radical 3I over 2. That's my standard form of this complex number. Example 2, again, start out by distributing. So you're going to distribute your -2 in. -2 cosine of -pi over 4 plus -2I sine of -pi over 4. So we're going to evaluate. Since -pi over 4 is on our unit circle, that's a -45-degree angle opening down. So I have 1, 1, square root of 2. And this is in the ASTC quadrant where cosine is going to be positive. So I have -2 cosine is adjacent over hypotenuse plus -2I times opposite over hypotenuse, and this time sine is negative because of the C quadrant. So I'm going to end up with negative times negative is going to be a positive 2I over square root of 2 and -2 over square root of 2. If you were to rationalize, or if you had used the song instead, you would have negative radical 2 plus radical 2 times I, which actually looks a lot more simple and would probably be preferable. I think most of you at this point are using the song rather than drawing the triangles every time. Okay, last piece for today, multiplying and dividing complex numbers. We have two formulas. You've got two complex numbers. We're calling them Z's. Z1, which has one R and a different theta, and Z2, which has a different R and a different theta. Okay, if you want to multiply those complex numbers together, you multiply the R's and you add their angles. If you want to divide the complex numbers, you divide their R's and you subtract their angles. And to me, this kind of intuitively makes sense. Multiplication and addition seem to go together, and division and subtraction seem to go together. So this is still in this general trig form. Your number out front just changes based on whether you're multiplying or dividing, and your theta just changes with either addition or subtraction. One thing in this division formula, your R2 can't be 0 because you can't divide by 0. It's a quick little number. So we've got a couple of quick examples and then we'll be done for today. Okay, so Z1 we have square root of 2 cosine of -pi over 4 plus I sine of -pi over 4 and, Z1, and Z2 10 cosine of pi over 3 plus I sine of pi over 3. So what we need to do to multiply them together is multiply their R's, so square root of 2 times 10, and then we're going to add their thetas. So we have cosine of -pi over 4 plus pi over 3 plus I sine -pi over 4 plus pi over 3. And of course you don't think that I'm going to let you leave it like that as fractions without being added together. So you're going to find a common denominator, which between a 4 and a 3 is going to be 12. So -pi over 4 we're going to rewrite as -3 pi over 12, and positive pi over 3 we're going to write as 4 pi over 12. So when I go to actually add those together, I'm going to end up with just 1 pi over 12. So I have cosine of pi over 12 plus I sine of pi over 12. Close that last parenthesis. Radical 2 times 10 isn't going to really simplify except to say 10 radical 2 in a little better order. We would have the option of actually distributing and multiplying this together to come up with a standard form. However, our directions have asked us to leave it in trig form, so once we get to this place, we are done. Then we divide by dividing our r's. You have to be very careful of division because multiplication order doesn't matter, but division it does. So if z1's on top, r1 goes on top. Square root of 2 over 10. Cosine, this time we're subtracting our angles, r1 or theta 1 minus theta 2. And I'm just going to go ahead and plug in the ones with the common denominator right away. So I'm going to have negative 3 pi over 12 minus 4 pi over 12 as my new angle, plus I sine negative 3 pi over 12 minus 4 pi over 12. I am okay if you are able to skip that step and just go straight to the answer. So I get square root of 2 over 10 cosine of negative 7 pi over 12 plus I sine of negative 7 pi over 12. That's my final answer in trig form. Example 2, last example for the day. Z1 and Z2, this time in degrees. It should be a little bit easier to add and subtract this time. Multiply them together. You multiply their r's, so 2 radical 2 times 6, and add their thetas. Cosine, if I add those together, I get 435 degrees. Two radical 2 times 6 can just be simplified to 12 radical 2. Cosine 435 plus I sine 435. Okay, so that's our trig form of multiplication. Then we divide, make sure you're going in the appropriate order. 2 radical 2 divided by 6. This time we subtract our angles. When you do 135 minus 300, because you have to go in the order that it was dividing, you're going to end up with negative 165. Okay, we can simplify out front. 2/6 can simplify to 1/3, so I have radical 2 over 3 cosine negative 165 plus I sine negative 165. That's my final answer in trig form. And that's it for today. Those are all the basics of complex numbers that we're going to need moving forward over the next several days.